Okay, so let's go over the answers to the first set of rates questions, the energy profile diagrams. Now, the first one we see is exactly the same as it is written in the question. So we're given delta H, negative 360. So the first thing we know is it's exothermic. So I'm going to draw an exothermic shape energy profile diagram with the products below the reactants. Next thing I'm going to do is to write in the reactants and the products, including the coefficients, of course. Now, reactants are always given a value of 0. Remember the units, of course. Activation energy is 30, so going up to plus 30 for the activation energy. Delta H is negative 360, so we go down to negative 360 for delta H. Now I always like to just mark in the particular values of significance. And even the energy released, which of course is going right from the top down to the bottom, which will be 390 kilojoules per mole. So that's for the first one. For the second one, we look to see how that equation relates to the original equation, which is of course is this one as well. So what have we done? We've flipped it back to front. That means exothermic becomes endothermic, and we've also doubled the number of moles. So 2 sodium oxides goes to 4 sodium oxides, etc. So I'm going to squeeze it in here. It's an endothermic energy profile diagram this time. So that means we've got the reactants and then the products are going to be higher. And the reactants this time are 4Na2O and the products 8Na2O2. See how important the coefficients are in this case. Reactants are going to be at 0. Now, reversing the reaction is like going backwards through the energy profile diagram. So, the activation energy for the reverse reaction is based on the energy released for the forward reaction. Now, if the energy released here, where we've got 2 moles of sodium oxide, is 390, then the activation energy here is going to be double that. So double 390 is 780. The delta H, of course, goes from being negative 360 to positive, and because we're doubling the moles, we'll be doubling the value of delta H. So that will be 720. And that also indicates that the energy released will have double the activation energy for the forward reaction, which will make it 60. Better get that correct. That's activation energy there. And marking those in, of course, which wasn't exactly asked for in question 1, it's always good to do though, makes it easy to work out activation energy and delta H as he's asked for in question 2. So activation energy is going to be 780. Energy released is going to be 60. And of course, for a neater version of all that, we've got the first energy profile diagram. We've got the second energy profile diagram for the reverse reaction, double the moles. And then the answers to question 2. Okay, going on to the questions for the multi-step reactions. We get the iron oxide reaction. So just the same as in the examples, we look for the common chemical between the two equations. Ignoring the oxygen, the common chemical this time is metallic iron, Fe. So we need to make sure we've got the same number of ions in both equations. And in this case, they're the two equations that are given to us. So we can draw them straight off without changing the moles. So my energy profile diagram is going to start off with iron at the top because both of these are exothermic. Both of the product levels are going to be well down. So we're going to have 2 Fe's on the top level. Then for FeO, we're going to come down to 272, negative 272. Then for Fe2O3, we're going to come all the way down to 826. And let's just get those units in. So, what's the question asking us for? The questions are, or question 2 is asking us for Fe2O to Fe2O3. So 2FeO here, down to Fe2O3 here. So that's pretty straightforward. It's simply going from here to here with the same number of moles. So we're going down, so it's going to be exothermic, and delta H is going to be the difference between those two. So we'll use black. Delta H will equal 826 minus negative 272, which equals, what's that going to be? 554, negative 554 kilojoules per mole. Okay, now the second question is going the other way. It's going from Fe2O3 up to FeO, but it's also doubling the moles. So we're going from 1 mole of Fe2O3 to 2. So we're going to be going in the up direction, and we're going to need to double our values. So let's just extend that line over a bit. So we're going to be going up, and delta H will be positive, and it's going to be 2 times the difference between the two, so 2 times 554, which equals, what's that, 1108 kilojoules per mole. Okay, so that's how I got there, and that Anita version of question 2. And that's Anita version of question 3. Okay, I hope you figured that out.